Continue, everyone. Did anyone think about why, if I put an iron nail in a copper sulfate solution, a reaction takes place? What's the reason?
Well, it must be that the potential is positive.
Right. So the overall potential is positive. So let's go to our table and look at the half reactions. So we have obviously iron. Yes, iron going to, where is iron? Elemental iron. Here's iron going to iron 3 plus. Alright, it's minus 0.03. There's also another possibility is that iron goes to iron 2 plus, minus 0.44. We're not sure which of those two, it could be iron 2 or iron 3. In fact, iron 3 is the most stable oxidation state. So chances are it's going to go to iron 3. Also, if you remember in the video, the reaction turned green. But this could be a sign that it's actually forming iron 3. Anyway, and what is the other half reaction? Copper going to copper 2 plus. There it is. So we've got plus, so copper going to copper 2 plus, sorry. Copper 2 plus going to form copper because the copper is being plated onto the iron and it's a copper sulfate solution. So that's the relevant half reaction and it's the right way around. So we end up with plus 0.34 volts for that. Alright, and then it really doesn't matter. It could either be that iron goes to iron 2 or iron 3. Either of these will still, notice, result in a, well no, actually, if iron goes to iron 2 plus, it would be, well, it will be positive. So both of those will result in a very positive potential. Do you see that? And hence it occurs spontaneously. If I do it the other way around, it wouldn't occur spontaneously, probably, because if you sum the potentials the other way around, you end up with a negative value. Now that brings me to my next point. We've now discussed that if the potential of an electrochemical couple is positive, that the reaction will occur spontaneously. Now this word spontaneous we've encountered somewhere before. Where? Gibbs-Helmholtz energy. Gibbs free energy. I remind you, the Gibbs free energy or the Gibbs-Helmholtz equation, delta G equals delta H minus T delta S. From thermodynamics, we know that if delta G for a reaction is positive, it is non-spontaneous. And if delta G for a reaction, the free energy change for a reaction, or the Gibbs free energy change is negative, it is spontaneous. Now there is a beautiful relation linking free energy change and potential of an electrochemical couple, like we've been dealing with. We can call them electrochemical couples. And the relation is simply, and this is a very important relation, delta G equals negative NFE couple. That little circle means standard conditions. So, this equation relates free energy change to the potential of a couple. In other words, what we've just been doing, summing the potentials of the half reactions, gives us the potential, the overall potential of the couple. F is something called the Faraday constant. The Faraday constant is a constant. It's a constant where it's basically the charge per mole of a substance, or of electrons, the charge per mole. So it's measured in coulombs per mole. And N, in this case, is the number of moles of electrons. So let's write that down. This is the Faraday constant. This is the number of moles of electrons. Now, the number of moles of electrons is very easy. You just get from the balanced half reaction. So if we take our copper wire in the silver nitrate scenario, the half reactions we said are copper goes to form copper 2 plus 2 electrons. Ag plus 2 electrons forms Ag. N, if I want to determine the free energy change of that reaction, N in this case is what? It's 2. 2. So the N value in that equation you get from the balanced half reaction, and this is N. Now, let's look at that equation. What is that equation telling us? Can someone tell me? It's a very important equation. What is it telling us? It's telling us that if we've got a positive potential, we're necessarily going to have a negative free energy change. Which means what? Yes. This is positive, N is positive, F is a positive constant, but there's a minus sign in front there. And so if I sum the two potentials of the two half reactions, and they happen to be negative, what does that necessarily mean the free energy is going to be? Positive, which means what? Exactly. So this beautiful equation links free energy with potential. And just a note on the units. Basically, N is the units for N is mole. The units for F, the Faraday constant, which is a constant, is in coulombs per mole, and E is in volts. So what do we end up with as a unit? We end up with, basically, it's going to be moles times coulombs per mole times volts. We end up with coulomb volts, which is what? Energy. Equals QV. That equation from electric fields, from physics. And so that's energy. So that's why it's expressed in joules. Okay. Now, that's a very important relation. And yes?
So if we say that the constant, not the constant, if we look at the reaction from the electron potential, we see that it's continuous because it's positive, right?
The potential,
Yeah.
yes.
And then if we put in the equation and the delta G, that makes sense.
It will necessarily be, if E is positive, it has to, the delta G will necessarily be
Yes.
positive because there's a negative sign there. All of these are positive, and so the result is negative.
Okay.
If E is negative, a negative and a negative is a positive, this will necessarily be positive and non-spontaneous.
Yeah.
So it makes sense.
Yes.
All right, now, so that's basically what I've written there. The Faraday constant has an actual value, so just you can therefore calculate the free energy change on electrochemical couple by plugging in the values. Now let's talk a little bit about electrochemistry. This is of course very important. We use it in batteries, for example. And using this knowledge that we've just created, if we have the right combination of, let's say, half reactions, the result is that we're going to get a positive potential. In other words, we're going to be generating electricity. We generated potential, a flow of electrons. And that's what electrochemistry is really all about. And to come back to this example of putting a metal in a copper in a solution, for example, like we just had copper in a silver nitrate solution, we end up with a spontaneous or non-spontaneous process. And if the process is spontaneous, we generate a positive EMF. Now we can actually use that to generate electricity. All right. So here we have an example. How could we do that? So how does that work? What this really is, this is essentially, we call it an electrochemical cell. It's basically a battery. All right? And it's making electrons. So I have a copper anode. Well, let's forget about anode and cathode at the moment. A piece of copper metal in a copper 2+ solution. I have a platinum electrode in an iron iron 3 plus iron 2 plus solution, and I have a salt bridge. Now the salt bridge is basically something that just closes the circuit, and typically we make potassium, we use potassium nitrate. Now if we actually build this thing up and attach a voltmeter, we will end up with a potential of plus 0.43 volts. And that you can do, you can actually go and just look in the table of electrode potentials. Basically, you have copper going to copper 2 plus, so this is one half reaction. And the half reaction between iron 3 plus and iron 2 plus, look at the potential, sum them, and you'll get a value of plus 0.43 volts. Now that's essentially a battery. It's generating electricity, and we call that an electrochemical cell. Okay, now the notation that we use when dealing with electrochemical cells is shown at the bottom here. We write basically the two half reactions with a double line between them, and that double line represents the salt bridge. So this is a new notation. So for an electrochemical cell, in other words, a battery, if you will, that's generating a potential, this is really what this is, again, is a very simple battery, ultimately. We write the relevant two half reactions, the oxidation half reaction on the left, the reduction half reaction on the right, with two parallel lines reflecting the salt bridge. Now I could build up another battery. I could build up another battery, right? Let's think about another battery. Let's think of another electrochemical cell. Let me draw one for you, and tell me what you think. So here's my salt bridge. Here are my two electrodes. Here is the voltmeter. All right, let's make this copper 2 plus solution, silver plus solution. First question. What's going to happen? Is there going to be a flow of electrons? Does this represent an electrochemical cell? Yes. We just saw that the reaction between silver and copper is essentially spontaneous. So what we're going to have is copper. We're going to have copper 2 plus, and silver plus, and silver. Okay? Yes. That's how we would represent the process going on here. What is the potential, what is the reading that I would see on the voltmeter? I think it was positive 0.46 or something, wasn't it?
Yeah.
So that's basically, it's as simple as that. So you must select partners, reaction partners, that when put together will generate a positive potential, right? And of course, if we take fluorine and lithium, for example, so the one right at the top of the table of electrode potentials and one right at the bottom, I'm going to get a huge potential. So you can vary the potential by changing the reaction partners. All right. The next thing is the notion of an anode and a cathode. Now, oxidation occurs at the anode and reduction occurs at the cathode. That's a definition I want you guys to know. Oxidation occurs at the anode, reduction occurs at the cathode. The way that I remember it is reduction with the T cathode. All right? So oxidation per definition is a process where we, what? Generate or use up electrons. Generate. So in this in this cell that I've drawn here, where is the anode? Fabian?
The example, the copper would be the...
Correct, this is the anode, because I'm generating electrons there. You see, copper is going to copper 2 plus 2 electrons. Those electrons are going to be generated, they go around, and then on this side, they're going to be available to be picked up by the silver, where the reduction is going to take place, and we're going to basically complete the cycle. So, complete the circuit. So this is going to be minus, this is going to be plus. So electrons are being generated here, and they come here, and then they get picked up by the silver plus. There's going to be a buildup of electrons on this electrode here, and the silver plus ions in solution are going to snap those up, and what's physically going to happen? In other words, if I build the circuit, and I leave it there, what experimental observation are you going to make? What's going to happen? What are you going to see?
The silver electron is going...
Louder?
It's getting bigger?
That's exactly. That is going to get big and fat because it's going to, as time goes by, exactly, the silver ions are going to plate onto this, and you're going to end up with a big fat electrode. And what's going to happen to the copper electrode? It's going to disappear. Because look what's happening. The copper is going to, look at this half reaction. It's essentially going to dissolve away in solution. What else are we going to see? Well, okay, the intensity of this is already copper, let's say a copper 2 plus solution. That's probably just going to increase in intensity, the color of blue, because I'm making more copper 2, so the concentration is going to increase there. And the reaction is going to essentially stop when there's no copper electrode left anymore. That's why batteries don't last forever, right? Because they get used up in a very similar way to what we see here. This is essentially a very simple battery. Okay, not a very efficient one, but it's a battery. It's generating electricity, ultimately. Okay, now, so that's oxidation occurs at the anode, reduction occurs at the cathode. We need a salt bridge. We can build it up in that way, like I've shown there, by a combination of metals, or I can build it up like I've shown here, where I have a platinum electrode, which is essentially inert. It doesn't really do anything, but in the solution, I have ions. So the electrochemical process takes place in solution. All right. So we can calculate the potential associated with this process this specific electrochemical cell here. So the copper is forming copper 2 plus. So if you calculate the potential, and the iron 3 plus and the iron 2 plus is, well, basically iron 3 is going to iron 2, copper is going to copper 2 plus. Write down the reactions, sum the potentials, and you get a value of plus 0.43. And you do this, in the same way as I showed you a moment ago when we were looking at that reaction of the piece of metal in the solution. You look at the table, you look at the direction of the reaction, write down the potential. If you swap it around, swap the sign around, and you simply add them up. If the result is positive, that's great. It means that we have a battery, a positive potential generating electricity, spontaneous reaction. If the reaction or the result is negative, it means no reaction.
Sorry, can you explain salt bridge again? Like, does that have any, is that participating at all?
Not at all.
What is that?
The salt bridge is really there to close the circuit, if you will, because essentially you can think of this as an electrical circuit, isn't it? And if you take the salt bridge out, you basically break the circuit. It's like having an electrical circuit and breaking the switch. There's going to be no flow of electrons anymore. That's the way I think of a salt bridge. The other role that it plays is that it ensures that there's a balance of charge in the system, right? So, and it does so by having potassium plus and NO3 minus ions, which can diffuse through these porous bridges into either, let's say, half reactions to ensure a balance. But basically, if you like, it closes the circuit, kind of. Okay, Right. Now, I now introduce the next notion. All right, this is what we've sort of looked at. I don't really want to. All right, we've looked at assigning the anode and the cathode. Oxidation occurs at the anode, reduction occurs at the cathode. That's not too important. Well, we've already looked at that. All right, now, I don't really want to discuss it. That's not so important. What I want to get to now, I mean, all I really want you to know from that, from all of those slides, is understanding, you know, essentially how a battery works, what an electrochemical cell is, how we put them together to generate a positive potential. Now, I just want to make one further comment, which is sort of reflected in the slides. What we've looked at now is a way of generating potential, right, from electrochemical half reactions. Sometimes the inverse of that is putting in electricity to do a electrochemical reaction. For example, if you take sodium chloride and you put 2 electrodes in it and you put electricity into it, molten sodium chloride, it's called the Dow process, you generate sodium metal. So that's the inverse of that, where you need to put electricity in to get the process going. So if you sum the 2 potentials like we've been doing and you get a positive result, that's good. The process is going to occur spontaneously. However, if you sum the potentials and you do not get a positive result, it means in order for that reaction to go, you need to put in electricity or potential. All right, and that's basically what I just had on these slides here. The difference between we call them galvanic and electrolytic cells. So basically, this is an example of a galvanic cell because it's occurring spontaneously. So electrochemical cells, you have galvanic cells and electrolytic cells. Galvanic cells are spontaneous, i.e. batteries, if you will, like we have here. And electrolytic cells are non-spontaneous. We need to pump electricity in to get the reaction to go. It's basically the take-home message of that. Yes?
Do we have that in the industry where we use electrolytic?
Oh, yes.
What can you do?
Well, for example, the Dow process, where they well, another example is the splitting of water. Right? If I want to split water, I can do so in a Hofmann's voltameter, which is an apparatus where I put electricity or I apply an overpotential, which basically splits water into hydrogen and oxygen. That's and that's if you look at the half reactions of water. Basically, well, that's basically what we're doing. Okay, it's unbalanced. Okay, let's just balance it. Let's put a half there, 2 and a 2. That's basically the overall, the net reaction. In order for this reaction to go, I need to apply an overpotential. Because if you look at the half reactions, well, if you look at the relevant half reactions, so H2 are going to form H+, and so on, the result is that you don't have a positive potential. You need to add electricity to split water. It doesn't occur spontaneously. Thank goodness it doesn't occur spontaneously, because then we wouldn't be here. You see how important this is? So that's an example of splitting water to generate hydrogen or oxygen. Well, to generate oxygen, sorry. Oxygen gas from electrolytically. Another one is, well, if you take sodium chloride and you melt it, and you put in 2 electrodes and you apply an overpotential, you generate sodium metal at one of the electrodes from sodium plus and chlorine gas at the other. But you need to apply an overpotential. Okay, but that's not so important. What's more important is what I'm going to discuss now. The last topic for today. A very important topic. And it's the so-called Nernst equation. Very, very important. So, the Nernst equation. Now, What is this all about? That table of electrochemical potentials that we've been using for the last time to do all these calculations and to determine if something is spontaneous or not was measured at standard conditions. 298 Kelvin, 25 Celsius, and very important, a concentration of 1 mole per decimeter cubed. Remember? That's why we have the little circle there. That circle, each circle, means at standard conditions. You've seen that little circle with enthalpy as well, and with free energy, delta G circle, delta H circle. Entropy, delta S circle. The circle in chemistry always means under standard conditions. Okay? The standard conditions in this case being, as we can see reflected in the table, reflected here, 298 Kelvin, 1 bar pressure, 1 atmosphere, 101.325 kPa, and 1 molar concentration. Now, obviously, if I build a cell with hydrogen on the standard hydrogen electrode on the one end, and a metal and a solution on the other to measure the potential, and I have a 2 molar, not a 1 molar solution, it's going to affect the potential, obviously. And that's what the Nernst equation is all about. The Nernst equation enables us to calculate what the potential would be of essentially an electrochemical cell or couple or whatever under non-standard conditions, which is very useful and important because we don't always work with 1 molar solutions. It's very restrictive, right? And so what the Nernst equation enables us to do is to get around that, and that is essentially the Nernst equation. There's 2 forms of the Nernst equation. Well, I mean, basically it's the same. You can express it as RT over NF. F is the Faraday constant. R is the ideal gas constant, 8.31, I think. T is the temperature in Kelvin. N is the number of moles of electrons. And at the bottom, this is just another form of the Nernst equation. You can use either, where we don't use the natural logarithm, we use log base 10. Now, what this equation is it's giving us the potential, the E cell, the potential of an electrochemical cell or an electrochemical couple, where we take the Q into consideration. So this is the electrochemical potential under standard conditions, and you can think of this term here as a sort of a corrective term. So it takes into consideration changes in the concentration, for example. So what is Q? What is Q? We encountered Q when we were discussing equilibrium. What is Q defined as? What?
Wasn't Q the constant where before it reached equilibrium?
Yes. Q was essentially mathematically equivalent to K, but it's something that we can use at any point in the reaction, not just at equilibrium. So you see what's happening here. Q, we don't use K, we use Q because it might be that the electrochemical cell is not at equilibrium, per se. Now let's take an example. Let's do this by way of example so you can see. Let's suppose I have, alright, so let's suppose I have a cell, an electrochemical cell, where I've got a copper, well, let's draw it. Let's draw it. Here's the cell. Here's the salt bridge. Here's the potential. Right, this is copper. This is a copper 2 plus solution. This is iron, and this is an iron 2 plus solution. Iron sulfate, copper sulfate, nitrate, whatever. The counter anion doesn't matter, it's a spectator. There it is. Now the question is, if the copper 2 plus concentration in the solution is 0,3, so notice not 1, 0,3, I've changed the concentration. What concentration of iron 2 plus, in other words, what concentration of iron 2 plus is needed so that the potential of the cell is 0,76? Now this is beautiful, because now we can tune by tuning the concentration, we can fine-tune the potential. We're not restricted to those potentials we see in the table. If I change the concentrations in these half cells here, I can change the overall potential. That's great. So let's look at the Nernst equation again. Quite frankly, this modification at the bottom here is, well, basically it's the same. I've just recalculated all of this and did a change of base to log 10 from natural log. It's essentially the same thing. This is, of course, the easiest form of the equation to use. So what are we actually trying to do here? We're trying to, the question is, what iron 2 plus concentration is needed so that I have that potential? All right, how do we proceed? Well, the first thing we do is we write down the two half reactions, and we write the net ionic equation, obviously. Now, from that cell that I've drawn there, obviously, iron is going to go to iron 2 plus, copper 2 plus is going to go to copper. If we look at the table of standard electrode potentials, and we sum the value of these two half reactions, in fact, let's do that. Let's go back to the table. There's the table. So the two half reactions, copper 2 plus, iron 2 plus iron, let's find them. There's copper 2 plus 3 electrons forms copper, 0.34, and iron 2, where is that? Can anyone see that? There it is. All right, so it's minus 0.44. So if we swap this one around, we're going to get a value of 0.78. Copper 2 plus 3 electrons forms copper, plus 0.34. Iron, so we swap that one around, goes because we want to get the most positive value. Iron goes to form iron 2 plus 3 electrons. Mine is going to be plus 0.44 because I'll swap it around. Does everyone follow? What's the overall potential, Katarina, under standard conditions of this electrochemical couple?
You have to add them, right?
Yes, yes. So it's going to be 0.34 plus what? Plus what? Yes, plus, which is what? 0.78. Now remember, that's what that value is. What is that? That is E circle cell. Circle meaning standard conditions. Right? This table is electrochemical potentials under standard conditions. So now let's go back to the Nernst equation, or to our problem. So we've now figured out that this is zero. So this is the Nernst equation. We want to get E cell to be 0.76. E0 cell we've just shown is 0.78. So what is N?
Sorry, 0.059. What was it?
0.059 is RT over NF, essentially, and I did a change of base here. It's just a simplified version of the Nernst equation here, right? It's essentially a constant. But you can use either, but this is the easiest form of it. All right, so what is N in this equation, guys? 2, yes, because if I balance two half reactions, iron goes to iron 2 plus 3 electrons, copper 2 plus 3 electrons forms copper. I'm transferring 2 moles of electrons. So N is 2. Now what is Q? Q, as we've said, is the reaction quotient. And the reaction quotient for this reaction is defined as, let's write it down. So this is the net reaction. Q, the reaction quotient, is going to be concentration of Fe2 plus over concentration of copper 2 plus. For the reaction quotient, I only take the species that are in solution. The copper on the right, on the product side, is a metal, and on the left, the iron is a metal, so that we don't take into consideration because it's not in solution. Because you can't measure the concentration of a solid, it's not in solution. And Q is about stuff in solution, concentrations. So the Q expression for this reaction is simply Fe2 plus over iron 2 plus. So let's go back to the problem. If copper 2 plus is 0.3, what Fe2 plus is needed so that E cell equals 0.76? Okay. Well, basically what we're going to do is we're just going to plug in the values and see what we get. So you can see that's what I've done here. 0.76 equals 0.78 minus 0.059 over 2 log 10Q. I solve for Q. And I get 4.7, right? Now we know that the initial copper concentration, we're told, is 0.3, so I solve for the iron 2 plus concentration. You must be able to work with logarithms to do this, everyone, please. And you get a value of 1,4. In other words, it's a simple matter of plugging in the variables into the Nernst equation and solving for the respective thing that you're looking for. You could also be asked to find, for example, what would the potential of the cell be if the concentration was 1.3 and 1.6. In other words, if I give you the concentrations, then you can calculate Q, plug in the values and get the E cell. There's always one variable that you'd have to calculate. But it's a very powerful equation because, as you can see, by changing the concentrations of the half cells, you tweak the potential slightly of the electrochemical cell, which is very useful. So we're not restricted to this table. We can vary the potentials, and that's basically how we do that. So that's the Nernst equation. And very important here, always remember E0 cell. That is the value you're going to get from the table of standard electrode potentials measured at 1 bar, 1 atmosphere, 298 Kelvin, etc., 1 molar concentration. And you can see from this example, by changing the concentrations from 1 molar to 0.3 and 1.4 respectively, I changed the potential to 0.76. I lowered the potential slightly. So if you're a scientist in an electrochemical company, and you want to build a cell that has a certain potential, exact potential, you can use the Nernst equation to figure out what ratio of concentrations you need in the half cell to get an exact, at least initial potential. Of course, what's going to happen, as this reaction proceeds, the concentrations are going to change and the potential is going to change. Now that's something for a more advanced electrochemical course. There are ways of dealing with that and looking at the effects of time and how the potential changes and stuff like that. So electrochemistry is a very important branch of chemistry as well. And yeah, it sort of pops up everywhere. So yeah, I think that's basically that. Is everyone happy? Any questions? So the Nernst equation, knowing the relationship between free energy and spontaneity in electrochemical processes, balancing redox reactions, determining potentials, it's all very important. Right, and basically, the first part of the lecture was really an introduction, just to get everyone on the same level. What's important is the stuff that appeared actually in the last 45 minutes, right? That's the sort of university level stuff that I expect you to know. Now let's talk about the final. It's on everything, of course. And how does everyone feel about that? I know, I sound like a psychotherapist. How does that make you feel? Actually, a lot of my friends say I should have become a psychotherapist. How does that make you feel? So how do you feel about the midterm? I mean about the final, sorry.
It's still a bit like kinetics for me, so it's always work on that.
Yeah, work on the kinetics. I know that's difficult, but you know, it's important. The exam is really very well divided between all the sections. There's a bit of everything. And yeah, I think it's doable, and I think most of you don't have too much to worry about. Most of you are going into the exam with a reasonably comfortable margin, right? So if you have a bad day, I'm not saying that you should take it easy, but I think with the tutorials, and I will post these grades, sort of your, let's say, your semester mark, if you will, your term grade, I will post shortly on Ilium, and then you can know what sort of margin you go into the exam with, right? The exam is next week, Thursday, I think, right? Monday? Oh my god. All right, well, I don't know that. I think, you see, I think this other course that I'm doing is Thursday. All right, well, 8:30, then we get it over and done with. And of course, I will grade them as quickly as I can and give you feedback. I will be available in my office this week, right? If you want to come by, particularly tomorrow, I'm in my office all day. Please come over if you want to discuss something. There's already 1 or 2 people that have made an appointment. And I'll be happy to assist you, right? If there are any questions. Today we have a tutorial, a post and a pre-discussion, and on Thursday, some of you might have noticed I posted an old exam paper with some questions that we might want to go through together in the last hour of the Thursday tutorial. So I think there's really no reason for you all to get 100%. Okay. So see you guys then on Monday morning 8:30 for an intellectual extravaganza.